Okay, it's about the time. I'm gonna go ahead and get started, even though that no one has showed up. I'm gonna go ahead and get this started, okay? And then I'm gonna record this one, and later on I'm gonna put this up in our website, okay? So let's see that you can easily see that what we are planning to do today. That in this third week we are planning to go through the chapter 10, confidence interval. Confidence interval and their use, because that earlier at a certain point, that when we were going through the point estimates, I mentioned that there is another branch of that estimates called the interval estimation. This is that. Okay, so I mentioned how to build this up, but at that moment I was talking about how to build up the confidence interval for population mean. When the population mean is unknown, you really need to estimate it. When you estimate, those estimate will appear in different form as a like an interval or as a like a the point, just a one single value or whole bunch of values. If you get a like a one value, then you're gonna say that that would be a the best estimate. Now on contrary to that one, you can remember that when we were trying to that build up that several y bars, so many y bars. Can you remember? Y bar would be that sample means not only one sample. Sample means several sample means we repeatedly that excuse me, computed or calculated by generating the different samples. Like for instance, that the most of the example that we had 1,000 samples from the 1,000 samples, we had the 1,000 sample means. Those 1,000 sample means were utilized. Okay, those 1,000 sample means are utilized to get a point estimate, as well as today we're going to talk about interval estimate. They both can be achieved through the same thing. What we did was we got that the sample means, we drew the histogram, we went to the center, or we found the mean of the means. Mean of sample mean would be a best estimate as like a point estimate for the unknown parameter population mean. But go beyond that one, we're gonna see that not only that, we can think about that some kind of that with a certain accuracy or certain tolerance. How could we gonna get some kind of that interval of estimates, whole bunch of estimates, not the everything we cannot take into account, because everything would not be useful. It's based on that how much confident that our population mean gonna be inside that parameter would be the the concept that we taken into account when we gonna construct the confidence interval and say what is the confidence that we have that those uh, unknown parameter gonna be within our the sample means. Based on that one, based on that accuracy tolerance, we're gonna determine that a certain number of sample means would be within this interval, not the whole thing. We can generate 1,000 samples. We're not going to take into account all the 1,000 samples. In the primary stage, for the point estimate, we took only one sample. Can you remember? Only one sample. One sample means, sorry, one sample mean. Then now beyond that one, we're going to get a certain number of sample means out of that 1,000 samples. That's the discussion we're going to build up over here. Why we really need to do that one? That's the discussion we have to build up over here, okay? In this chapter 10, they were talking about why we really need to do that, okay? So let's go ahead and look at this, how this can be built up piece by piece, okay? Piece by piece, how this can be built up piece by piece. So beyond that, okay, I'm gonna go back to what we had in the beginning, okay? Let's say that uh, we have, okay, is the discussion. We have, see, it's the population, okay? Population. You have an unknown parameter, which is population mean denoted by mu, okay? Mean. Mu you don't know. mu. You have no clue about mu. Okay. So what we did was we pick samples. Can you remember? We generate sample one of, let's say that size n equals 157, thinking that population of this the data would be what? Data would be fingers data. Okay. I'm gonna use the fingers data. Okay. Sample this one. Then you calculated y bar 1. See? Y bar 1. Y would be what? Arm length. Arm length has been abbreviated as thumb. See? Then you went to the second sample. See? Sample 2 of size n equals 157 and y bar 2. See? Then at the same time, we have a observed sample. Can you remember? Sample of size n equals 157. I would call that y bar obs. Okay. That value we know. And we keep going. Let's say sample 1000. Sample m equals 1000 of size n equals 157. Okay. Y bar 1000. Okay. This y bars are generated by either bootstrapping or by bootstrapping, by either bootstrapping or simulation, by simulating. Okay, bootstrapping or simulating. And y bars are varying. They are varying. See? They are varying. So you have a see y bar 1, y bar 2, dot, 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 y bar obs, okay, dot, 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 y bar m equals 1000 are varying. And they will be, see, graphically displayed in a histogram. They can graphically display in a histogram. You know how to do that. Okay, we know how to do that. Okay? Those codes we know already. Okay, so we don't have to worry about that. And we know simulation code, we know this code, we know. Okay, this code we know. Okay, histogram code we know. Okay, everything we know. So we get the rough idea what's going on here. See, now I'm gonna go ahead and put this one. Y bar mean sample mean. See, sample mean. So here I have the frequency f. Okay, so when I draw the histogram, look like what? Symmetric distribution, you can remember. Something like that. Then you're gonna draw the smooth curve scheme in the top of that one. See, then I go to the center. Center. Mean the mean. How do you denote mean? Mean is a mu y bar. Mu y bar. You can remember mu sub y bar. Mu sub y bar. Since it's not available, you can go to its observed value. Sorry, estimated value. Estimated. This one is not good. Should have been. Delete this one. Yeah. So this should be same as population mean. That's what the population means. See? Population mean. Population mean. Population mean. Population mean. In population mean is not available, we're gonna go its estimate. Estimate of population mean. That's what we are trying to do in the middle. We are trying to find the population mean estimate. Since it's not available. That's why we got all the sample mean, and from that one, instead of going to the one sample based on one sample, we are trying to get a mean of the sample means histogram. And then from that one, if you get the center of that one, or that average of all these sample means, that would give you a better estimate rather than you're gonna pick like a sample mean based on one sample. This can be replaced by y bar. See, so y bar can be replaced by y bar of observed value. See, that's done. So in addition to that one, you have here what? The spread. Spread is nothing but the standard deviation. Standard deviation is sigma y bar. See? Sigma y bar is nothing but sigma over square root 10. So sigma is not available. I'm going to use its estimate. See? Sigma hat over square root 10. That means sample standard deviation. Sample standard deviation will be replaced by the observed sample deviation divided by square root 10. You see, you have a spread, you have this. Now we know that this center, that's what how we're going to build up this discussion. Theoretically, the center of the sample distribution should be mu. Okay, look at now. I'm going to do this one. See, this is theoretical. Okay, I'm going to add something here. Theoretically or abstractly. The center of the sampling distribution. Center of the sampling distribution should be what? Mu y bar, mu sub y bar, which is theoretically should be population mean. Okay, theoretical. Population mean. Okay. But empirically, okay, empirically, see, look at this one. I'm going to add something to here. Empirically, practically, or experimentally, see, the center of the sampling distribution. See, the center of the sampling distribution equals to this one. See, that empirical. This one empirically. This one theoretically. See, So you have this one. Theoretically, you have this one. But when you get, how could we know theoretically? If you know theoretically that this one, by previous experiment, somebody might have done this one and he might have that population mean in his hand. Based on our experiment, see, we have this one for the given samples. I got the y bar obs only. That would be the center. But these not the same. They both not the same. They differ. That's why we replace this one with that one. In another way, I can say approximately, see this one. See, approximately, see. Approximately. We can take this out approximately. See. Now what are you gonna do? I'm gonna see how that my empirical one is differ from, by how much my empirical one is differ from the theoretical one. See, by how much? See? Empirical tenth is off. See, on the theoretical center. It's called the error. See, they both not gonna be the same. There might be some kind of slight difference. Okay, error. It's called the error. So error is nothing but difference between what and what? Y bar obs and your population mean. See? That's the error. E absolute value, because you can see subtract either way. Y bar obs minus this one, no, that difference for the error. See? The higher the spread of the sampling distribution, the lower the higher the error. Sorry. The higher the error, see, the higher the, if it is lower, it's also lower. See? They are proportional. See, directly proportional. See, they are directly proportional. Directly proportional. They are directly proportional. So that gap create an error. So we can say, therefore, therefore, the standard deviation of the sampling distribution can be used as a tool to quantify by the error incurred by estimating the unknown population mean is mean. See, the standard deviation is, see, the spread means nothing but the sample standard deviation. So the higher the spread, the higher the error. So higher the spread, higher the error. So in that sense, this error that incurred by estimating the unknown parameter mu can be maximum and minimum. See, then we are not interested in minimum error, we are interested in a maximum error. In that way, we can easily tackle that one. We can easily remedy that one. Okay. So let's go to the maximum error. Maximum error, which is called the margin of error. Okay? Margin of error, which is like MOE. They say nothing but okay, nothing but okay, critical value of Z or T distributions. Okay, critical value. We're gonna talk about that one later on. C or T distribution. There are two distributions I'm gonna use. And standard deviation of the sampling distribution. I'm sampling distribution. So that means critical value of C or T distributions, the distribution times standard of the standard deviation sampling distribution means standard deviation of y bar. That means it's nothing but margin of error, maximum error that can incur. I'm gonna say CC or TC okay, times sigma y bar. Okay. From here, I'm gonna split into two. Margin of error becomes, if you use CC, sigma over square root 10 you can use. Sigma is known, you can use that one. Sigma is known. See? Sigma is known. N is large. You can use this one. See? N large. Sigma is known. N is large. Regardless of it. Okay. Regardless of it. Regardless of it, you can use it. But sigma is unknown. Sigma is unknown. You have to use it for the margin of error, nothing but TC, T distribution times, T distribution times, okay, we're going to talk about that. TC times S over square root 10. You can put the S means obsess, okay, obsess. Okay. When N is what? N is N less than 30. Let's say N is greater than or equals to 30. For margin of error, you can use either. Okay. Either one. See? Margin of error can be either TC S subs over square root N or margin of error is TC S subs over square root N. See? Since you are using that this particular large values, see, large values, it can be either this or that, okay, this or that. So let's see, we keep going. I have to show you this one at a certain point. Let's see. See. So I'm going to draw this now. How the T distribution and C distribution. Either they both look the same. Okay. I'm going to draw this one. So I'm going to draw this one for you to see clearly. So get in. See. First you have a see something like this. It's a T distribution. Okay. You can say T distribution. It's pretty much similar to, very similar to that C distribution or normal distribution. Bell shape, symmetry. Okay. You have at the center, you have a 0, see, bell shape and symmetry. And is decided by its degrees of freedom. Degrees of freedom. Let's say we have a, see, and an example, let's say 10. Okay. Degrees of freedom, that many degrees of freedom you really need to tell. So that's why they put the T like this way sometimes, see, TDF. DF equals 10, see, for distribution. See? T distribution, we're gonna write like that. It's center. See, this is center. See, you don't have to worry about the spread. We can talk about the spread. See, look at now systematically, if it is getting higher peakedness, higher peakedness means what? What's gonna happen? It's trying to get like a that see it see that lopsided around the center, lopsided around the center. So what's gonna happen? See, it's getting see higher peakedness. If you increase the degrees of freedom, gonna go like this. Go down. Okay. This one is like what? This one I can say T distribution, degrees of freedom, like if you increase to 20 distribution. See? Okay. T distribution. Just keep increasing that our degrees of freedom. Okay. Let's say what's gonna happen. See? See? It's trying to get the higher peakedness. See? But thin tail, thin tail. It had a thick tail. See? Can you remember? In the beginning, thick tail. See? The beginning, we had a thick tail. See? This one, thick tail. See? This. See? See? On both side, okay? On either side, okay? I'm just doing this one on one side, thick tail. Later on, what happens? See? Later on, see? Then what? It's getting thinner now, see? See? Thin tail. See? Thin tail. It's getting thinner and thinner. But the higher peakedness, see? Peakedness is getting larger and larger, see? So this one, see? See? Thinner tail. Thinner but higher peakedness. If you keep this one, we can say this T degrees of freedom, let's say 100 distribution. If you increase, if you keep going this one, and if you're gonna increase this one infinitely, large. Okay, infinitely large. So I would say, see, you keep going, see, keep going. Then this one, like this, see, like that. See, this one is like what? See, this one, see, 1, 2, 3 for the continuation. This is a degree, this is a T distribution with the degrees of freedom equals to infinity. So infinity, see. Then we're gonna call this one what? Then we can call C distribution, normal distribution. See? Normal distribution. See? So T distribution. I'm sorry. The degrees of freedom, infinity symbol, see, is same as normal distribution. Distribution, see. So they both the same. That's why interchangeably we are using C and T. This one you can say C distribution. Okay. So that's the part that we have to take in account. See, sigma known, regardless of n, you can use this one. Sigma is unknown, small sample, you use this one. Large sample, you can use either one. Large sample, sigma unknown, but large sample with the aid of the sample mean, sample standard deviation, you can see this one, this one, this one, or this one. Okay. Sigma y bar can be see, based on that one, actually, this one, okay? And they both will be tackled at the same time. Okay, I have to write this on one more step. CC or TC. Oh, we don't need that one. It depends on that uh, sigma known unknown that we already wrote that one. So you don't have to worry about that one. So our margin of error look like this. This is maximum error. That incurred error is nothing but the difference between this one. See? See? Difference between this one. See? This error should be within what? Within margin of error. Error should be within margin of error. Error should be less than or equals to, see? Error should be less than or equals to what? Margin of error, maximum error, no? We know that now. So error, the error, right here, error has to be less than or equals to what? Maximum error. Absolute error. Let's say like that. Absolute error. Absolute error. Less than or error. So therefore, error should be what? This one, see? Between what? Minus maximum error. Maximum error when you take out the absolute value. I'm sorry, plus maximum error and minus maximum error. within that, see, plus and minus. See, should be within that. Error is nothing but what? Y bar, let's say mu minus y bar ops. Okay, I'm gonna write that one. Either way I can write. Less than or equals to what? This one maximum error is nothing but margin of error. This one minus margin of error. And I'm gonna keep the mu in the middle. See, y bar, I'm gonna take both this one plus margin of error. Y bar ops minus margin of error. See, should be between those two. Okay. That's what called the confidence interval. See, that's the same thing. See, it has to be within that. That's the one that I'm gonna, well, that's the one that I'm gonna write this way. Confidence interval for mu should be between y bar minus MOE all the way up to y bar plus MOE. See? The same thing. Interval. That's another way of writing. See? The first way of writing, second way of writing. CI. See? Would say confidence interval for the unknown population mean. Okay? Mean. Even by that one. See? See? Or some people, they prefer to write that this way. Confidence interval for this guy is y bar, I'm sorry, ops, y bar ops plus or minus margin of error. See, another way of writing. It's a third way of writing. See? Then we better go ahead and you can see that both ways work. Confidence interval for this mu can be right y bar ops plus or minus CC, see, confidence interval from that distribution over sigma over square root n, see, or same as y bar ops plus or minus s ops over square root n, see, it's the same thing, see, like this. Or you can write like this way. Confidence interval for mu is y bar ops minus CC sigma over square root n, comma, y bar ops plus CC sigma over square root n. Bracket means interval. See, or y bar ops minus CC s ops over square root n, comma, y bar ops plus CC s ops over square root n. See, still the same. See, either way. See? Like that. If you want, you can write like a brackets with the bracket like an interval. See? Like an interval. See? Interval s ops. See? Like that. Or the other one, see? You can write the confidence interval mu y bar ops plus or minus, okay, plus or minus TC S ops for sure over square root n, or y bar ops minus TC S ops based on that which one you're going to use, y bar ops plus TC S ops over square root n, bracket Like, other way, right? See, with the aid of T, the other one with the aid of C. This one you don't have to try it in two ways. See, see, okay, so many ways of writing. So that's what we're gonna call that this another way of writing. See, some people they write like this way, regardless of your the confidence interval. See, lower bound of mu, upper bound of mu. See, lower bound of mu, comma, upper bound of mu. See, this is another way of writing. Another way of writing. Where lower bound is nothing but see, lower bound would be of mu would be nothing but y bar of plus or minus margin of error. Sorry, minus only, not plus. Margin of error. Or y bar of minus CC sigma over square root 10 critical values and y bar of minus CC S subs over square root 10. See? Or y bar of minus TC S subs over square root 10. See? Again, based on that. And similar fashion, you can write upper bound of mu is nothing but y bar of plus margin of error. See? Margin of error. Y bar plus margin of error. See? See? Or you can say y bar of plus CC sigma over square root 10 y bar of plus CC S subs over square root 10 depends on what you have. Okay, y bar see, of plus TC S subs over square root 10. Either way is fine. You can write in any way. See? Now we have to figure out that what are you going to get for that margin of error. Then this one, confidence interval. See, we can get this done easily using what? See? Easily using that in R, we can easily get this done. Okay, we're going to learn about that one. Okay, so and how could you going to get the CC? Let's look at the critical value. How to get the critical values? Okay, critical values, little bit. Okay, critical values. CC and TC. See, they believe. See, let's go to the first one. CC. See, you have a CC over here. See, we're gonna think. See, this C is nothing but related to y bars. Okay, related to y bars. Related to y bars. This is the standardized distribution of y bar distribution, sampling distribution. Okay, y bar distributions, the standardized one. Okay, standardized one. We believe, see, we believe the center should be mu. How far this can go? See, oh, mu. It should be mu. See, but I have what? Y bar of. See, I have this one. See, This is theoretical. See? Theoretical. This one is what? Empirical. See? Empirical. See? Empirical. Practical. That one. You can remember. See? Practically you get a vibe of. It should have been mu. Okay? But we don't know how far that can go. They decide it can go up to in C distribution. Okay? C distribution, they consider this one is 0. Okay? This 0. It's gonna go to here, CC. Up to here. It's gonna go to CC here. Minus CC here. Cutoff value. Critical value. This area is given by certain percentage. Let's say 0.95 or 95%. See? 95% confidence region. This one called the confidence region. See? Confidence region. Region. See? Confidence region. Within that region, you have to get the values that can be supposed to be that assigned for mu. Okay. So the critical value is completely based on given a certain, we have a certain that values are very standard value. Okay, we can have a look at it, those values. Okay, I can give you, or we can find it too, doesn't matter. Okay, very fine. Then I can see this one. See this one. How do you find this? See, this one you can easily find. Go to Q norm, nar, Q norm, and then you put what? Area to the left of that. Area to the left is how much? Then this one is how much? This one is point, see, 0.5, 0.05, see, 0.05. We are left over with the 0.05 and 0.025, 0.025. This one 0.025. Area to the left, you know, area to the left is how much? 0.9, 0.9, 975, 95 plus 0.025. Okay, this one, see, this one is 0.950 plus 0.025. Okay. That's how we got the 0.975. That value, if you go ahead and then punch that value would be what? 0.025 would be 1.95. Okay. 1.95. And if you want this one, again, we're gonna do Q norm. Okay, Q norm. Area to the left, Q norm. Area to the left is the 0.025. If you get this one, you're gonna get negative 1.9. Sorry, 95. Negative 1.95. See? So these are the cutoff values. 95. See? See? You can easily find that one. So if you do this one for different that values, this 0.95, we're gonna call that one confidence value. confidence coefficient. How confident, okay? How confident your interval would be. So confidence coefficient. Nothing but I would write, I denote that by, see, confidence, I would like to denote by 1 minus alpha. Alpha, okay? 1 minus alpha for reason, okay? 1 minus alpha is nothing but the probability that the population mean fall within the given confidence interval. How many of them gonna fall within that confidence interval is that probability, or that proportion is called the confidence coefficient. That means, let's say that you construct it, this is your population mean, population mean, population mean. Let's say you construct 100, see, you constructed 100 confidence intervals for mu. See, let's say mu will be included. See, included. Most of them included. But see, some of them are excluded. How many of them going to get excluded? 95 will be included. See, 5 will be excluded. See, they don't include that mean. See, those are the confidence interval. Okay, those are the confidence interval. They include this one, but 1, 2, 3, 4, 4, and 5. See, see, 95 confidence interval will contain 95 confidence interval will contain population mean mu, while 5 of them do not do so. You construct the 100 confidence interval. Out of 100 confidence interval, can you construct 100? Yes. That's what called the coefficient. How many will contain this? Why? Why of them do not do so? See, so 1 is a 2, 3, 4, 1, 2, 3, 4, 5. I think I have an extra one. 1, 2, 3, 4. So we don't need. See, they don't include. See, this is like a confidence interval. See, this is the confidence interval for mu. First one is the confidence interval Q for second one. See, and you keep going. See, keep going. Let's say that this is the last one. See, this is the confidence interval for mu, 95th one. See, 95th one. See. So that's what we call the confidence. See? That's what we call the 95 confidence interval. See? 95 confidence. 1, 2, all the way up to 19th one. See, this should come. See, dot, 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 dot. And then we come dot, dot, dot. That confidence interval will contain, will contain 95 out of 100, 95%, 95 will contain the population mean called the confidence coefficient. Confidence coefficient has been given by 1 minus alpha. That's the notation. If you know the confidence coefficient, based on that one, you can build the confidence. And confidence intervals counterpart called the level of significance. Okay, something over here. Alpha, see? Level of significance. Level of significance means alpha. We're going to talk about that one when we go through that testing of hypothesis. Okay. Then we can come to its counterpart, confidence coefficient. It is 1 minus alpha. Then we're going to come to what? Critical value of C. The standard one. CC. Let's say this one is 0.10. This is 90%. See, this one 0.05. This one we can say 0.95. This one 0.02. This one 98 confidence coefficient. This one 0.01, 0.99 confidence. Let's say what are their values. This one 1.64. This one 1.95. This one 2.32. This one 2.57. See? So now we don't have to worry about that one. See? Critical value will be given. See? If you want, they will be given. See? So there are several ways we can get this done. See? Confidence into. See? But when it comes to that R program, in our program, look at, we'll connect this one to our homework. Look at homework number 3. See? 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 I'm going to connect this one to our homework, okay? So at a certain point, I'm going to say, this can be done in several ways, okay? Let's say, okay. Okay, before that one, I can go into some. So that's kind of like a, how to build the now, how you gonna construct the confidence interval? Let's look at that. How do you construct the confidence interval? How do you construct the confidence interval? You can get this done in various ways. By simulation, by bootstrapping. Okay, by bootstrapping, by this one, the way that we do that formula. This is just the one of the method. But the theory has been basically built up through this one. Okay? Theory has been basically built up through this one. Okay? So let's see that how to construct the confidence interval for that given any level, any coefficient. What is the confidence interval means? That whole bunch of y bars, whole bunch of y bars, whole bunch of y bars. We have generated so many y bars, but out of so many, how many y bars will be taken into account? The discussion here. Okay? The discussion here. Okay? So, excuse me. So let's try to build up this discussion. Okay. Let's try to build that. Okay, construction of confidence interval. Construction of confidence interval. Okay, see, first one we can construct by bootstrapping. Bootstrap sampling distribution. So the bootstrap sampling distribution. We're gonna bootstrap, okay? Through the bootstrap sampling distribution, we can build this up. Or we can call that a bootstrap confidence interval. Okay, bootstrap confidence interval. Bootstrap confidence interval. So we can go ahead and bootstrap. Boot sampling distribution of mean doing by do 1000 times. See? Mean, get the mean. You can remember, go to resample. See? Okay, resample. You go to the fingers. Okay, based on that example, go to thumb, comma, 157, comma, close. See, that's how you're going to build up the boot sampling distribution. Boot sampling distribution of means. You know that one. You already did this one. Okay. Now if you want, you can draw the, but you can draw histogram. See, how do you draw histogram? Go to GF histogram. See, of mean. See, see, and you have a data frame. Data frame is nothing but the boot sampling distribution of them. Okay, you can fill this one. Let's say dark blue. Okay, and you can link this one with the link operator or pipe operator, link or pipe operator. Okay, and you can put the labels. Let's, you can get the title, bootstrap sampling distribution, sampling distribution, sorry, of means, of means with n equals 157. See, and close it. Okay, then what? Then this, you're gonna connect this one, and you can draw the density curve, GF density. If you want a density, you can say color, orange, and then you need the what? Density curve. You need the approximate normal curve. Then you go to GF dist. You're gonna say I need the normal distribution. Then you can give the color, dark orange. Then you give the parameters. Parameters will be given. You go to the list, you need the mean. You're gonna get the mean. How do you get the mean? You go to thumb, or you're gonna go to favorite stat and then get that one. And go to, sorry, you go to fingers, not the thumb, you go to the fingers, data, fingers data, and then go to thumb and find the mean. And then same way you can do the standard deviation. Go to fingers, go to thumb, close it, close it, list one, and param. See, histogram. Once you generate, once you generate, look at, once you generate this one, what do you have? Y bar 1, Y bar 2, Y bar 3, dot, dot, dot. See? See? Y bar 998, Y bar 999, Y bar 1000. Okay. Now what are you going to do? Now you're going to rearrange, okay? Arrange Y bars in an ascending order. Okay. Or descending order, ascending or descending order, doesn't matter. Descending order. How do you do that one? I'm going to ascend in order and put it back into the same thing. I'm going to arrange. Arrange function will do that one. You go to the what? Data frame, boot, SD, OM, then you go to what? Variable. Okay. You go to variable. So this is the data frame. Yes, the data frame is the variable. Okay. They will be arranged. See? Will be arranged in ascending or descending order. Then I have what? I have order statistics now. See? Those are called order statistics. Look at how I'm going to write. Minimum value comes first. It's not that first the data entry, not first Y bar, not going to be the minimum value. Now, once you arrange, first one is Y bar 1. See, look at how I write first order statistics. See, that's the minimum. Minimum we call the first order statistic. See? Then you have the second order. See, second highest one. And the third highest one. Look at, I put it in. See? That's not the same as the Y bar, these ones. They've been rearranged. See? When you rearrange, I'm going to use this one. Then Y bar. See? 998 point. Y bar 999 point. Y bar 1001 is nothing but the max. It's called the 100,000th order statistic. Order statistic. Now what I'm going to do? Now what I'm going to do, I don't need the critical value. I'm going to get this one. See, you saw that this Y bar, see, you saw that one Y bar being arranged. See, Y bar, okay. Look at this Y bar. So I'm going to start in from here. Y bar 1, Y bar 2, then Y bar 3, dot, 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 then Y bar 998, Y bar 999, and Y bar 1000. 1000 like that. We can remember, we can draw the histogram for this one. See? And draw the histogram. Draw the histogram for that. See? See? Like that. See? So we can get the see two curves. See? One is going up. One is going like this. See? That's the density curve. See? That's another curve. Another curve. See? Smooth curves. You need the approximate curve. See? See? This one approximate normal curve. See? This one, density curve. Sometimes we're gonna call this on the kernel. Kernel. See? Now what? Now I'm gonna think, okay, from out of this one, which one would be the 95th one gonna be in the middle? All of out of these y bars, I need the 95th confidence interval. See, 95th one. So let's say that something like that. Okay. I'm gonna say this one to this one here. See, this one under that curve. See, let's say okay. See? I'm gonna larger for my convenience. Okay, large. Okay. So this one is 0.95 or 95% confidence coefficient. If that's the case, I have to find out which y bar upper and lower would be that my cutoff value. Okay. Then what is my lower bound for mu? See, what is my upper bound for mu? See, how do you find it? You have a y bar. See? You have a y bar. See, up to this side, it's been rearranged from what? 0.025 to this side, the leftover 0.025 to this one. See, the leftover under the curve. See, so you know that the 25th one, you come in from the minimum value, go all the way up to and then hit this point. See, that point would be what? How much that point would be? See, 1000 times how much to the left over, how much to the area to the left. So that would be y bar. This one is nothing but 25. See, 25. See, oh, see. This is the 25th order statistic of y bar. See, or another name I'm gonna do this one. 25th quantile of y bar. See, 25th quantile. That means out of y bars, I'm gonna pick the 25th one. In a similar fashion, y bar, I have 1000. See, 1000 y bar. I'm gonna take area to the left is how much? 0.95 plus 0.025. See, this one is nothing but area to the left of lower bound. And this one is 0.975. This one is nothing but area to the left of upper bound of mu. See, which is y bar how much? 975. 9/5 one. See, so this one is 9/75 order statistic of y bar. Okay. So this one, this is related to this one. There's nothing but 975th what? Quantile of y bar. See, those are the upper and lower bound. Those are the upper and lower bound. So LB, how do you get this one? Now we know that one is that one. So lower bound of mu is nothing but y bar 25th order statistic. How do you get this one? I'm gonna go to the boot sampling distribution of mean and say, please give me the what 25th one. See, this one, see, if you go to boot, see, if you go to boot, you do like that. Or you go to boot, sampling distribution, and then go to means. Then go to means. Then you don't need that vector, that matrix form. See, that's how you're gonna get it. See, then upper bound of mu is nothing but y 975th order statistics. How do you get it? You go to the boot SD ordered one. Okay, this is already ordered 975th, and see, come on this one. Or you go to boot sampling district this one, and then go to mean. If you go like straight, go to mean 975. See, so you get the upper bound, you get the lower bound. Once you get that one, now you can write confidence interval for mu at the level of 0.95. See, which is lower bound of mu, comma, bound of mu. Once you find that one, plug in over there. You can plug in over there. This is how you're going to find it. In order to find this one, bootstrapping through the bootstrap. Look at, you get the Y bars, you generate, you arrange, see? You arrange, once you generate, you have this one. Once you arrange it, you have this one. See? Then you're gonna order. See? Then you have like this. See? See? This is how you're gonna arrange. See? Then what? Then you go ahead and find it. Your bounds, upper bound and the lower bound. See? Upper bound and the lower bound. See? Lower bound. Then see? This one, you're gonna get the upper bound. See? Then upper and lower bound, you can easily get it from. Next, do this one. So here we were telling about that, okay, at a certain point. So that upper homework, I'm sorry, I'm gonna go ahead and then make the homework available. Okay, and quiz. Contents. Okay. Contents. E3. Okay, this one. Open. Please open. So you can see easily now. Okay. This is the homework. The homework. Okay. This is the data set related to this one. This data download from kaggle.com site that now is open database. This specific data set. Okay. Breast cancer Wisconsin diagnostic data set from the Kaggle website. Here, features are computed from a digitized image of a fine needle aspirate FNA of a breast mass. They describe the characteristics of the cell nuclei present in the image. Blah blah blah. This is the article. This data set is also available through this one. Also can be found on UCI machine learning repository as well. So see, diagnosis, malignant and benign. 10 real value features are computed for each cell nucleus. each cell nucleus, 10 are computed. Okay. Radius, mean distance from the central point of the perimeter, texture, perimeter, areas, movement, compactness, concavity. The mean, standard error, and worst or large. And for those things, again, when you measure that one, you got the mean of this one. Mean of mean, standard error, and the worst or largest. Mean of the three largest values of these features were computed for each image, resulting in 30 features, because we have 10 variables. For each and every variable, we have done the mean radius, mean texture, mean mean text, mean radius, standard error of the radius, worst or largest, mean of the three largest values. Mean of the three largest value called the largest, see? And largest of radius. So you have every feature has three categories, three measurements. You go to the radius, means the mean distance. Those mean distances will be put together and get the mean, standard error. First, largest mean of the three largest value for each one. In that way, we create a 30. And the result in 30. For instance, field 3 is the mean radius, field 13 is the radius standard error of the radius, and field 23 is the worst radius. All feature values are recorded with the 4 significant digits. Missing attribute value none. Class distribution 357 benign, 212 malignant. So descriptive statistics, perimeter mean, texture mean. Create a histogram, see, for the perimeter mean and texture mean. See? See? Interpret the correlation between the perimeter mean and the texture mean. See? Correlation. Then what? Then you have to find the confidence interval correlation too. I'm going to come to that one too. Before that one, for the mean, let's look for the mean one. See? Perimeter estimate. Parameter estimate means just the parameter. What are the parameter estimates? See? Find an empty model for the parameter mean. If you empty model, your mean would be that perimeter mean. Perimeter mean, the average of the perimeter mean. Perimeter mean is one of the features here. See? Perimeter. Where's the perimeter? See? Perimeter. See? You get the perimeter. Perimeter has a perimeter mean, perimeter standard error, perimeter worst. So they say the perimeter mean. See? Let's get the data set. Diagnosis. There are two types, malignant or benign. See? The mean of the perimeter, area mean, smoothness mean, see, concavity, see. So this mean, see, the radius mean means like radius has been for this particular patient, see, radius has been measured several times and got the average. Okay. And radius standard error is same, see. Radius standard error is nothing but the standard deviation of that measurement. So that's the average. Radius. Radius is the what? Radius is nothing but it's the average. See, mean of the distances from the center of the point. See, it's the mean. Then you get the radius. You measure several times, you get that radius. See, those radius, see, will have their mean. See, radius, you're gonna measure the radius. See, but the mean of the distance from the center to the point on the perimeter, you did that one several times. See, there's a point to that one. See, you measure this one several times, got the mean, and then you're gonna measure this radius so many times. Mean of the radius. When you get to the mean of the radius, you have the standard deviation for that. See, texture, standard deviation of the grayscale value. See, texture. They have the mean and standard deviation too. Everything has a mean and their own standard deviation called the standard error. Okay. Standard error. Standard error. So they're gonna ask us to do. So especially this one, fit on the slope. I'm not gonna go to that one because since we are here for the mean, yeah, fit an empty model for the perimeter mean, number 3, and provide the 95 confidence interval around your parameter estimate. Around your parameter estimate, you're going to provide the confidence interval for whom? Let's see. Number 3. Number 3. Yeah. See? Number 3, the one I tackle. Okay. I tackle this one in different way. See, my perimeter means to have you have a perimeter. Perimeter means like a perimeter. Perimeter. See, it has been measured several times, and then you get this average for the same particular person. Okay, particular person. Every person has their perimeter mean. Every person has the perimeter standard deviation, which is called the standard error. Everybody has that largest reading, 3 largest reading, and then get the average of that one, which is called the which is called worst. Okay, worst. So I'm gonna go ahead and then fit in this one. Okay, I'm gonna go ahead that data in. Okay, systematically do this one. Let's see. Effect size, mosaic, LSR, supernova. Let's see what's going on. Data. I, not I. E in N 6. Let's say October. I'm sorry, November. 2022. Homework 3. And set that one. And data read. String. You have see summary, number of row, how many patients? 569 patients. Out of 569, 357 has been identified as benign, healthy patients, 212 malignant, disease patients, then 559, 569, 569, 569, and number of columns should be 32, including that 30 plus diagnosis and the ID. See, these two. And the rest would be that 10 variables. They've been repeated 3 times in a different, for the different specification like mean, standard error, standard deviation, and the worst. Okay. So I got that one. Let's say that, let me try, give a try. I don't know, mess up. This is the problem. I hope that it will be installed. Okay, it's running right now. Let's get the library now. No. Okay, yes. Yeah, if you're gonna restart this one, the others will be gone. That's okay. But let's go to Q3, question number 3. See, you're gonna fit in this one into an empty model. Get the perimeter, sorry, number 3. Okay. Fit an empty model for perimeter mean. That variable. See, perimeter mean will be model with the empty model. See, this is nothing but the average of the perimeter mean. See, summary, if you want, you can go to summary too. That will show you the point estimate, standard error. See, p-value. Now you're getting familiarized with something like this. Standard error and estimate. If you know this estimate, if you know standard error, then get the z-value. And we built up the confidence interval. Yes, but we don't go in that route for time being. I'm trying to kind of see, they see, then supernova, if you want to go to supernova to empty model, it's a different thing. And I'm using the bootstrap method. See, look at the bootstrap. I'm trying to find the confidence interval for population perimeter mean. See, population perimeter mean. That's my idea. Okay. So here, part C, they say, part B, A, B. What is pre? Pre you can interpret, okay, by running. Here, I'm on part C. Confidence interval around your parameter estimate. For whom? So I'm trying to write, see, construction of confidence interval for the perimeter mean. Population, everybody, population, perimeter mean, perimeter mean, perimeter mean. Perimeter mean. The method 1. I'm trying to construction of confidence interval for the population perimeter mean. Okay. Okay, I'm gonna okay. Okay, then I'm gonna share this one. Okay, sorry about that. Okay, so now you can see. Okay, let's go ahead and run the. Okay, let's go ahead and run this one. Okay, so confidence interval, I have 569. I go to data, perimeter, resample. See, head, bootstrap. See, these are the perimeter means. Then arrange. Then I arrange and put it back. And arrange and I go ahead and find the LB lower bound, which is bootstrap means 25th one. See, 89.976. And another way to do that one. See, another way to an upper bound, 975th one, upper bound. Oh, I had to say here 95% confidence interval. Okay, 95% confidence interval. Then upper bound, two ways you can get it done. Okay, upper bound and lower bound. Okay. Then CI, CI, upper script, superscript, you're going to put 0.95. And subscript, you put mu. Nothing but mu is nothing but population mean. See, population perimeter mean. I'm sorry, population perimeter mean. Population perimeter mean of the population perimeter mean. Perimeter mean is my variable. See? Which is bracket. I can put lower bound. See? LB. Simply I can say LB of mu upper bound. What are these? So I can see comment out. So equals so much lower bound point. This one control comma upper bound. See, any value in between this one can be taken as a point estimate for that. See, that's the confidence of 0.95. So, see, and the second method was simulated sampling distribution of y bar. Simulated method. Second method. See, simulated method. Second method. See, we can simulate this. See? If you simulate this, that's a kind of like a same procedure. See, same procedure. Second method. See, second method that you can say simulated sampling distribution. See, simulated sampling distribution. Okay. How do you do that one? Sim sampling distribution of mean given by do this one, assuming that they were coming from normal distribution, mean, see, mean will be taken of random numbers R norm 157. See, in that particular example, okay. Because on book I'm writing my example, that homework I do based on that homework, okay? And for the mean would be nothing but go to Thumbstat and get the mean from there. And for the standard deviation, go to Thumbstat, get the standard deviation, close there. Thumbstat given by favorite stats of the data fingers. And then you can draw the histogram and you can get the, then you have a sim one, then you're gonna rearrange. Okay, then you have see y bar 1, y bar 2, y bar 99, 999, y bar 1000. See, then what are you gonna do? Then you will rearrange and put it back to this one. Sim sampling distribution of mean, arrange sim SDM, go to the data and pick the variable mean. Once you see arrange, you have y bar 1, y bar 2, y bar 999, y bar 1000 within this is the max value. Okay, is the minimum. See? Minimum to maximum. See? Then you can get the lower bound and upper bound easily. See, so confidence interval 0.95 is same like earlier. You get the upper bound and lower bound. How do you get? Go to the sim sampling distribution of mu and get the 25th. Okay. Comma this one. Okay, if you go to this one. And simulation is DOM 975. That's it. Right. That's how you're gonna get that. That's how you're gonna get that 0.95. You are confident that your population mean will contain 95 times. If you can construct 100 of them, it is 1000. How many gonna contain? See, 950. 195,950. 950 of y bars will contain over there. Then you need the lower bound and upper bound. See? See? That one, so see, it's in a similar fashion. See? So we go ahead and then generate this one. See? See? Here, arrange, get the lower bound. Two ways we can get. See? See? Then get the upper bound. See? If you use the mean, you get this one. See? 9377. See? It's pretty much the same. See? Same thing. Pretty much the same. See? And you can see copy. I'm gonna put here. See? I mean, of this one is nothing but 89 points. See? Pretty similar. This value 89. This one, it's not gonna. Everybody's not gonna get the same value. Okay, it differs. Okay, whatever I got with this simulation, I'm gonna put it here. Okay. Then what's the third method? Normally distributed. The normal distribution. See, using the normal distribution. What that means? Let's say go to third method. I'm gonna go to third method. Can you remember third method one is already done? Third method one is the one that we already done. See, that's the one that we did. See? Using normal distribution. Using normal distribution. Using normal distribution. Using t distribution. See? Third one. Normally distributed sampling distribution. With the aid of that one, sampling distribution, we're gonna build up the confidence interval. Normally distribution, you know that. Then we have see the aid of this one, y bar here. It should be theoretically, see, theoretically should be what? Mu. Empirically should be what? Y bar ops. And there is a gap, that gap called the array. And this one is nothing but the space. See, we're talking about the center. Center now you're gonna view in two ways. In the beginning you thought that it should be that mu. Then later on mu will be replaced by y bar or obs, but approximately. Now we're gonna go ahead and see that what their difference would be. That difference has to be tackled. That difference will be taken into account when we're gonna talk about the interval estimate. State. See, standard deviation. Sigma of y bar. Sigma over square root 10. Or S subs over square root 10. Okay? With the aid of this one, you already know confidence interval. Confidence interval for mu 4.95. Nothing but y bar ops plus or minus. Okay. Margin of error. That one is nothing but plus or minus CC S subs over square root 10. Okay. Then we can build up the lower and upper bound separately. Okay. Lower bound of mu is y bar of minus CC S of over square root 10. Let's see how to get this one using our this one R code. Okay, in R, see how do you get y bars? Go to thumbstat in this example. Okay, thumbstat and go to me. See that minus. How do you get the CC? If it is 95%, you know, if you from the table you can put the 95%, 1.95, or you can calculate Q norm. See, Q norm area to the left. It's negative. Can you remember 0.025 area to the left times. Then standard deviation is nothing but times stat. Go to that one, standard deviation divided by QRT of, go to thumbstat and get n. No, get 10. Q stands for quantile. Critical value. This is for normal distribution. See, normal quantiles. You can get that. See, you can use that. Sorry, lower bound. See, in a similar fashion, you can do the upper bound as well. See, upper bound is nothing but its counterpart. Thumb length, thumbstat, go to mean plus you know, you can put a 0.975 times Hampstead, go to standard deviation, QRT, Hampstead, N, Hampstead N. Okay, Hampstead N. Okay, so let's go ahead and okay. I'm just working on a little bit. I think that so much material being covered, but that's okay. You're not gonna miss anything, Magnus, because that everything has been that already recorded. Okay, I just jump into that this homework. The homework is now available. Homework 3. Okay, I just related to what I'm talking about. That one I'm here. Question number 3. Okay, based on this given data. Based on this given data, okay, you can see it's a massive data set with several variables, okay, 30 variables plus these two, whether that particular person is malignant or benign or the cancerous or non-cancerous like that, a healthy or patient, healthy or deceased. For that one, we are built-in up interval estimate, not the point estimate, around the parameter estimate. That means that I'm talking about this population. See, if I go back a little bit to that, you can easily catch up. I come from here, see, little bit, see. So I have a, see, this is a discussion that when you have unknown parameter, let's say the finger state, the population, I'm interested in the thumb length, population thumb length. Then the population thumb length can be inferred or estimated with the aid of one sample. But later on, we broaden our knowledge and we decided no, one sample is not enough for us to that think about that our best estimate. That's why we went to several samples. When you built up the several samples, based on that one, we have different sample means. See, different sample means that variation has to be taken into account. How do you generate this one? By using the bootstrapping or simulating. We talk about 2 methods even in the last week. See? Then Y bars are generated by either bootstrapping or this one. Then Y bars are varying. These are varying. That means these Y bar 1, Y2, Y bar obs. Obs also over there. Observed value. M equals 1000 are varying and they will be graphically displayed in a histogram. You know how to do this and you know how to get the bootstrapping, you know how to get the simulation, you know how to draw the histogram. So then what happened was when you draw the histogram for sample mean spread is okay. Standard deviation sigma y bar, sigma was square root 10, then sigma is unknown. I'm going to replace this one with the sigma hat over square root 10. Sigma hat is nothing but the sample standard deviation. Sample standard deviation means there are many sample standard deviation, the simulated ones, but we're going to go to the observed one and divide by square root 10. But now we're going to looking into this our setup in a different way. I'm going to tell this one empirically, sorry, let's say theoretically, when you draw the sampling distribution of mean, this is the sampling distribution of mean, its center should have the population mean, which is we are trying to estimate. Whatever we are trying to estimate will come into the center of this our sample, that all the estimates mean. All the estimates mean, because instead of one estimate, we have many estimates. Out of that one, center would be theoretically mean. But practically, empirically, practically, experimentally, my center is not mu. Center is nothing but y bar obs. See? observed y bar. See, this is what you are expecting. This is what you got. Look at that. Means at this stage, earlier we didn't look at that way. Now we're gonna broaden our knowledge and then try to build up some that error term into this discussion, because of that you are expecting this one, this is what you got. They're not the same. There's a difference between those two. That's what we refer to as the error. See, empirical center and the theoretical center differ from each other. There are gaps. The difference is called error. That error is, that means the higher the spread of the sample, higher the error is. See, higher the spread of the sampling distribution, higher the error is. See, this gap is more, because that you theoretically you think center would be here. If you get a huge spread, your sometime y bar should be somewhere here. Then gap is very huge. That means you can easily utilize the standard deviation of the sampling distribution to quantify the error term. Okay? Quantify error term, that one. Then we're going to think about what's the maximum error that can incur by estimating this. It's nothing but margin of error. Margin of error is nothing but something called the critical value of Z distribution or T distribution times the standard error, standard deviation of the sampling distribution, which is critical value of Z or T distribution, standard deviation of Y bar, standard deviation Y bar is sigma Y bar, CC or TC, critical value of normal distribution or critical value of T distribution. We're going to, for the first time, introduce another distribution at this stage. This value will be based on what we know. Sigma is known and sigma unknown. If sigma known, regardless of n, you can say your maximum error margin of error is CC. You are using this one. Sigma over square root 10. Sigma you have to use because sigma is unknown. Known. But it is unknown based on your large sample or small sample, you're going to utilize T or Z. If it is small sample, you definitely unknown and small sample, there's no choice. You have to go to T distribution. Critical value from T. It's nothing but because you don't know sigma, then sigma can be replaced by S obs divided by square root. But if it is a large sample, even the sigma unknown, since you are dealing with large sample, still you can use the Z, but with the replacement of S obs, no sigma. And this one definitely T can be utilized. That's the discussion we are built in now. That's one way of constructing confidence interval. This is the normal distribution, how you get the normal distribution through the T distribution. What their relationship? They come in from the same family of distribution. So this is when we have a very thick tail in the beginning, see, flatten, thick tail, and flat, see, very flattened, see, see, your kurtosis, actually kurtosis, peakedness, see, very flat, but thick tail. And that will be determined by degrees of freedom. How many degrees of freedom? Let's say 10 degrees of freedom you have, you look like this one for T distribution. You're going to increase that one. It has to be characterized by the degrees of freedom. So they say 20. It's getting peak, see? Higher peak, but getting a thin tail. See? Tail becoming thinner and thinner while it's getting higher peak. If you keep including this one, now 100 degrees of freedom, keep going, and then if you're going to get the degrees of freedom infinitely large, that means if you are using a huge sample, n is large. See, this is nothing but n minus 1. You know, degrees of freedom is n minus 1. This is getting infinitely large. That becomes a normal distribution. See, T distribution, when the T distribution with the degrees of freedom, infinitely large degrees of freedom, is nothing but the normal distribution. That's how they are related. So now you can say error. Look at error. Error has to be less than or equals to maximum error for sure. It cannot exceed that one. See, your error, because you have an absolute error. That absolute value, if you have a, this is like absolute inequality, then error should be within what? Minus maximum error and plus maximum error. That means my maximum error is minus margin of error and plus margin of error. This is my mu minus y bar. I keep the mu in the center and get the y bar to both sides. So this is how we call that. See, mu has to be between this end and that end. This end and that end. Or some people prefer to like this way, condense this one, y bar ups plus or minus margin of error. Some people like this way, y bar ups minus margin of error, comma, this one. Some people, they prefer to write like this way. See? The margin of error will be replaced like this way. Some people like, see, spreading out like this. Some people use the t based on that situation, or spreading out like this. Some people like to put lower bound and upper bound. So many ways we can write the confidence interval for mu. See, this stand for CI stand for confidence interval. Confidence interval for the unknown population mean, which is mu. See, see, so many ways people see. Lower bound is nothing but y bar x minus MOE. MO is this one, or this one, or this one. Upper bound the similar fashion with the plus sign. Okay. Then we have a question that what the critical value would be. Critical value is decided based on the confidence coefficient. Whether you have to be provided with some kind of a level of confidence in which that your upper bound and lower bound can be determined. Because this is the confidence region, this is the likely region. These are unlikely region on either side on tail. That cutoff value, the threshold value is called the critical value. How do you get by R? Go to Q norm, put the area to the left. Area to the left is how much? I'm talking about 95% confidence interval. 95% confidence, 95 is called the confidence coefficient. See, confidence coefficient. So the tail will equally carry that the same weight, 0.025, 0.025. Area to the left is 0.975. 975 is nothing but 0.90, 0.90 and 0.025 being added together. That's how you got that. Okay. That's how you get that. Okay. Then that value is, if you run that one, you get 1.95. If you do this one for the same area to the left of that cutoff value, this thing. And on the other hand, confidence coefficient is denoted by 1 minus alpha. That's the probability that the population mean fall within the given confidence interval. See how they're going to fall. Let's say that you constructed 100 confidence interval for mean. Out of 100, your 95 confidence will contain the population mean, while 5 of them do not do so. See, everything included, except for this guy, this guy, this guy, this guy, this guy, and this guy. 5 of them not going to be include this mean. They were off. That we're going to count how many confidence interval, the percentage of confidence interval that would contain the unknown population parameter is called the confidence coefficient or the probability. Okay? So denoted by 1 minus alpha. See, later on we built up the table. The alpha called the level of significance. We're going to talk about that one under the test in Harvard. This is a confidence coefficient. This is a critical value of C. CC. If it is 0.90% confident, 1.64, 0.95, 1.95, 0.98, 2.32, 0.99, 2.67. These are critical value, standard one. If there is like a unstandard value, it's easy. Q norm, put to the Q norm and find the area to the left. Keep that confidence region in the middle at the center and go to its bound. Those bound will be determined by this one or by this table. If you have a 10%, 90% in the middle, you have 1.64 minus and plus minus that one. That's the value you're going to bring it down and then plug in over here. Then under this discussion, there are several ways you can build up the confidence interval. First method, bootstrap. See, you build up bootstrapping sampling. With the aid of the bootstrap sampling distribution, I can build up the confidence interval for me. Since this is based on that example, see, I built up the bootstrap sampling distribution and draw the histogram. See? And then I get these values. I'm going to arrange them now, ascending order. How do you arrange? By using the same boot standard deviation of sampling distribution of mean and the mean and arrange. And once you arrange, we're going to call them the order statistics. Because here you don't know which one is the minimum value. But here what we're going to do by arranging, you for sure know this is the minimum value. The last one was the maximum value. The first value I'm going to write within that the subscript within parentheses. See? When you write like that, we're going to call them the order statistics. First one called the first order statistics, which is the minimum value. And this is the second largest, third largest. We see? Let's say this is 5, this is 10, 15, see, 100, 103 like that. And then this is the maximum value, 1 or 10, see, thousandth order statistics. If you arrange that one, from that one, keeping the 95%, you have to find the cutoff value, not based on the critical value. There's no the critical value coming from the normal distribution because these are bootstrapping. We're going to calculate which y bar would be the mine lower bound, which y bar would be the my upper bound. See, lower bound is nothing but y bar. I have a 1000 y bars. How much area to the left of that one? 0.025, that means 25. Then 25th order statistics would be my lower bound. In a similar fashion, 1000 times 0.975 area to the left. I'm talking about that y bar, which y bar would be taking 975th order statistics. Get this one. Get this one. How do you get that one on this one? See, go to bootstrap, that my sampling distribution. 25th one, comma. If you straight go to without mean, you comma and then leave space here. But if you go to the mean, you don't have to do anything. See, two ways you can get this done. Similar fashion, you're going to get the 97th one and 97. Either this way and write the confidence interval. That's what I did for question number 3. I'm here. See, fit an empty model. Once you empty model, perimeter mean has a mean. Okay, this is the variable name that has a mean, grand mean. So you find the confidence interval around that guy. Y bar. Y bar is not enough now. Y bar is not enough. I need this is what's gonna happen. Related to this one, if I draw the graph for you to see very clearly. This is exactly what's gonna happen. See, you have a variable called y variable named perimeter mean. Okay, y is nothing but perimeter mean. Okay, this is my response variable, response one, which is quantitative. See, oh sorry, quantitative. See? But on x-axis, there's nothing. You see, no x bars. That's called the empty model. Once you draw, you're gonna get this one. We had that discussion. See, y bar. Now I prefer to call this one not y bar. From now on, I call the y bar obs. See, y bar obs. Do I know the y bar obs for this particular example? That this perimeter mean? Do we know that one y bar obs? Yes, you can go to, see, I run this one. Mean of the perimeter mean. Part C, construction of this one. Perimeter mean. Simply perimeter mean, nothing. So I'm gonna run here. 91.96903. Let's see. 91.91. 96,903. Okay, that's the absurd value. But now on, I don't need, I'm not happy with that. This is called the point estimate. I need interval estimate. I need the lower bound to upper bound. See, I need like this. See, I need this one. I need the upper low. This I'm gonna call the lower bound of mu. I need the upper bound of mu. See, I need a whole bunch of values, not only this center. See, I need the whole bunch. That's what I'm trying to do at this for this discussion. See, I need a whole bunch of values. See? How do you get the lower bound? Lower bound is based on the given confidence-free value. I can get that one. That's why they say for this guy, find the confidence interval around that parameter, around the parameter estimate. See, around the parameter estimate. Parameter is the mu. Estimated is y bar. Y bar is replaced by y bar. See, around this one. How do you find it? That's what we are trying to do over here. See, number 3. See, we get this one. 91.97. They go by the 91.97. This will be approximated by 91.97. See, enter. See, see, but that's not enough. I need this guy and this guy, lower bound and upper bound. Okay. First method, bootstrapping. See, I bootstrap. I have 569. I go to resample. I go to that data and I get my variables and how many I'm going to generate one at a time. See, head, see, generated. Then I'm going to arrange and put it back and find the lower bound. How? Go to the mean. If you go to mean, you don't have to put a comma. See, lower bound. See, like that. Or if you don't put that one, if you straight go to data frame of the bootstrap distribution, see, pretty much the same thing. Same thing. And upper bound the same way. See, 2 ways you can get that one. You don't need this one. It's coming from the same. Then you can say confidence interval for C is a superscript. This the subscript, lower bound, upper bound, right there. See? It's the same thing at the end of the day. I'm gonna write here, see. It's confidence interval for mu of the level of 0.95, nothing but lower bound of mu, comma, the bound of mu. I found lower bound is 89.969, 89.96986. I found upper bound 94.00346. Okay. My observed value gonna fall within that one. Okay. I built up that one without even y bar. Look at that's the interesting part. I didn't utilize this one to get the upper and lower bound. That's a one way of getting this done. That's a one route. Look at, I didn't use that one. So I'm on the third method, but if I go back to that example, see, I didn't use anything. I just see order statistics and got the 25th one, and no critical values, nothing. See? See? I didn't utilize this one to add plus or minus like that. But bootstrap got the upper cutoff, lower cutoff, upper cutoff and lower cutoff. See? See? This one, see? So then, see? This 0.96 or see? So it's gonna be in between. See, you're gonna write this one, then lower bound and upper bound. That's it. That's all you have to do. You have to write 89.96986, 94 point, oh, sorry, not writing numbers, no, 94.00346 bracket. I use the bracket to indicate that endpoints are included in this interval. That's it. That's how you're gonna run. This one, see, number 3, question number 3, part C. That's a one way to get it done. Then I was talking about the second method. Here. Second method through the simulation. See, simulated method. See, simulation. Then not the bootstrapping. Let's do the simulation method. See, that's the one part. Second method. Let's go to how to simulate. See, method 2, using simulator sampling distribution of y by assuming that perimeter mean is normally distributed. See, perimeter normally. Sim. Okay. Sim STOM. See, R norm 569 with the mean and standard deviation. Head arrange lower bound, upper bound another way. See, you can get the lower bound this way or this way. See, then upper bound this way or this way. And similar fashion, lower bound this way or this way. Upper bound this way, this way. You come up with the same, pretty much the same answers. It is between around 89 to 93 or 90 to 94. See? Then the third method is the one that I'm talking about here. Third method. Third one is the based on the one that I did earlier. See, normally distributed, assuming that you normally distribute sampling. This is straightforward. That's the one that we talk about in the very beginning. See, using this formula. See, using this formula, plus or minus, so you can separate and talk about it. Then I'm finding that one. See, lower bound. See, I'm finding lower bound. In the similar fashion, see, lower bound. In R, how lower bound, how do you get that one? See, in then upper bound will be, see, LB of, sorry, UB of mu equals y bar of plus GC sampling, observed sampling distribution, observed, observed this way, see, this one, so this one. See? So you go to see y bar, how the thumbstat, you build up the thumbstat and go to mean minus Q norm area to the left of that one. See, thumbstat standard deviation, go to square root of that one. See, you use the formula and plus that one, same thing. That's the same thing we are planning to do over here. So before that, I'm going to go ahead and get the stat. I'm going to call that one favorite stats for the perimeter mean, data called data. I'm going to call this one model stats. And statistics are here. So margin of error, if you want, you can build up the margin of error is nothing but Q norm, okay, 0.975 plus 1, I'm going to build up 0.975 standard deviation of whose standard deviation, see, one way of getting that one, sigma, see, go to data, perimeter mean, divided by square root of the model stat 10. Can you remember sigma over square root 10? S subs, see, go to this one, standard deviation of the perimeter mean, see, go to the data, go to the perimeter mean, or go to the favorite stat. If you want, you can go to the favorite stat too. Okay. I'm gonna write this one in another way, that the way that I have written. Okay. The margin of error is nothing but Q norm SD. Rather than SD, I'm gonna write the way that I have written here. See, go to thermostat like that. Is there a thermostat? I would say I'm gonna go to Q norm model stat. Okay, go to model dot stats model dot stats. From that one, I'm gonna go to the standard deviation. And that should be divided by square root of model stating, or this way. Doesn't matter, so many ways. Then upper bound is nothing but see, this one. See, mean, go to this one plus mean O. You can do the same thing. See? Copy. You can go to the what? Go to the model stat, dot stats, and then go to mean. And you don't need this one plus margin of error. See? Come on. See? 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 Model stat plus margin of error. You don't have to go to that one. See, with the margin of error, you can do this way or this way. But the lower bound I wrote with the one method. You can do this one in any method. But anyhow, see, if you run to this one, see, you get the margin of error. See, the Q norm, upper bound, lower bound, pretty much the same thing. Same thing. Now, instead of that one, okay, I'm gonna just do the T and then I'm gonna stop here and then we can next time we have to jump to the other class. This one little bit I'm gonna do T distribution. That's the fourth method. See, instead of normally distributed, you can use the T distribution. T distribution method as well. See, that's the fourth method. See, fourth method I'm gonna say T distributed sampling distribution. See? Sampling distribution look like a T distribution. See? T distribution. See? Let's say, see? Your Y bar, see? Y bar. See? Your center 0. See? Then you're going to think about this should be given by degrees of freedom. Its degrees of freedom is nothing but n minus 1, 157 minus 1, which is 156. See? With the aid of that one. How do you write the lower bound of that one? Lower bound of mu? Nothing but y bar ops minus margin of error, y bar ops minus TC S ops square root 10, excuse me. This one is the thermostat. Can you remember thermostat in R thermostat minus TC. How do you get the TC? See, TC is nothing but you go to QT, quantile of T distribution. Then you're going to put the area to the left, which is 0.425, because see, this is 0.95 here. I'm looking for TC minus TC. This area is 0.025. Okay, this area is 0.025. See, this is the confidence region we are working on. The area to this one is 0.025. Not only that, you have to give the degrees of freedom. Degrees of freedom is 156. See, close it. Times stats. See, stats. Go to standard deviation divided by square root. Go to thermostat. Okay. and go to N. See? See? Then similar fashion, see, you can write, see, the same thing. See? Quantile T in the same way that you can write the upper bound with the plus sign. That's not a big deal. See? The bound of mu is nothing but y bar of, see, plus margin of error. That means y bar of plus TC S sub, definitely S sub divided by square root. In R, how? Sumstat, see? Go to mean plus QT. Area to the left is how much? 0.975. Degrees of freedom is how much? 156 times. Go to Sumstat. And then go to ST divided by SQRT. The Sumstat. And then go to N. See? This is in R. Upper bound and lower bound you have, you can easily write the confidence interval. So the similar fashion, let's try this one and then we can stop. So I'm gonna do, see, we're gonna do model stat. We have that one. We know that one, see, already. See, I'm gonna write the margin of error. QT 0.975 degrees of freedom is nothing but go to the model stats in -1. You don't have to do anything. You have to recall them. Standard deviation of this one divided by square root of this guy. See, you built up the margin of error, which is that one. Upper bound is nothing but mean plus margin of error. See, still get the same answer. Lower bound, you minus margin of error, still the same. See, see, same thing. And the okay, let's since we come to that straightforward one, let's go to the confint. See, you can use the, see, confint by doing what? First go to the confint default function. See, confint function. See, parameter mean null model. You already run null model, empty model. See, and use the confint default on the empty model. You have to give the level how much. See, see, like that. That will give you confidence interval one shot. See, 2.5 to the left of that one, 97.5 to the left of that one. See, which is 89 to 93 again. But if you use the confint model, by default, that you are using what? Same as method 3. Same as method 3. Method 3 is what? Method 3 is nothing but normally distributed method. See? This method. See? 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 This method is tackled by the fifth method. Okay, this one, confint on your model. See? The other one is the sixth method for the fourth method, t-distribution. Sorry. Okay, then using the confint dot default function. See? Then next one, confint only. That means you are using the t-distribution. Okay, look at that. Confint. See? That's the same thing. The confint means you are using t-distribution. See? It's same as the fourth method. I'm going to write it down next time. Right there. Then there's a seventh method, last one called the 90, 68, 95, 97 rule. See? Based on that one, we can get this done too. Then we can talk about that. See, you don't need the critical value. Critical value is 2 parameters. See, 2. 1.96 is not a 1.96. We take it straight go to 2. Because based on this rule, because the 95 means within 2 standard deviations. You can put 2. See, same thing. See? See? But we're gonna go through this one in detail next time. So that's for the mean only. This discussion we're gonna expand to correlation coefficient, tree, slope, and intercept. pretty much everything. For everything, whatever that estimate you have found, we can build up the confidence interval. That's the broader discussion. We continue this one next time, and then Wednesday and Thursday we can finish the homework because it's a very lengthy homework again. See, so much over there, but when it comes to the answers, we like to, okay, you don't have to answer with all the method, but better off to learn all the techniques in that, see. But my answer key is very lengthy. That doesn't matter. You can just narrow down to whatever you want to write down, and then major thing that I want you guys to learn this material and they get familiarized with the coding and everything at the primary stage rather than then we do the testing or anything. That's not the proper way of doing things, but I think we are on the right track. But discuss with you and then get the answers for this question in that you can familiarize you. Okay. See? And even the this one too, that Cohen's D2, confidence interval 4. We are not have, we don't go to, we pretty much gonna go to all that confidence intervals. All type of, okay. Okay, do you have any question? If not, I'm gonna stop over here. Then have a good night, stay safe and be well, and then see you on Wednesday and Thursday. Okay, take care. Have a good night. Okay, thank you. Bye bye. Thank you very much. Okay, take care. Thank you. Good night. Thank you very much. You can watch that video. I'm gonna upload once it's processed. Okay, take care. Thank you very much.